Okay, we're going to start by looking at independent and dependent events. So two events are independent if the occurrence of one has no influence on the probability of the occurrence of the other. So an example of this is if we flip a penny and a nickel, so two separate coins, and we get tails for both, right? The fact that the penny came up as tails has no bearing. It doesn't affect at all the likelihood that the nickel comes up as tails. So it's just sort of happenstance that they both came up tails. I will say that it's important to be careful about thinking solely in a practical fashion. So really going back to the probability is important. So with the coin example, right, both the penny and the nickel independently, they have a 50% chance of coming up tails, 50% chance of coming up heads. And again, one coming up does not alter that 50% at all. So we can go back to the probability and make sure that hasn't changed. If two events are not independent, we call those dependent events. So a little example, and again, this one is more practical, but we can apply probability to it as well. So Charlotte experiences a snowstorm and Charlotte Airport cancels many flights. So are there days on which many flights get canceled where there aren't snowstorms? Sure, there's probably some other type of storm or something else going on. But these two events clearly have an effect on each other. So if there is a snowstorm, the likelihood of a flight getting canceled is clearly going to change since the dynamics of flying in a storm, especially in an area that isn't used to it, right, changes the scenario, the circumstances. So the probability is altered there. Okay, so those are sort of just the general idea. For conditional probability, we're going to have a slightly more formal way of looking at, how do we know if two events truly are independent? So before we get to there, let's just talk about what a conditional probability is. So the biggest thing is we recognize these as conditional probabilities when we see this kind of language, A given B, right? Given being the operative word here. A and B are generic events, but we know that this could be involving, rolling some dice or tossing coins, selecting a card out of a deck, those kinds of things. So we say the probability of A given B, and we write P of A with the vertical bar here, B. So A, that vertical bar is going to take the place of the word given. So A given B. And the way that we find that is we say, okay, well, let's find the overlap. What's the probability that both events occur? Probability of A and B. And then we're going to divide by the probability of B. Basically, what this bottom part is doing is it's saying, well, if B is the given portion, then we have to narrow our scope. We have to basically say we have a much smaller sample space now. So instead of all outcomes being likely, all outcomes being possible, we're only looking at the cases where B has already occurred. So we need to narrow down by the probability of B already occurring, and then tack on A being a part of that. So that's just a conditional probability. I'm going to come back to the part where we address independent in just a moment. So let's look at a conditional example here. So suppose we roll two dice, and for the sake of kind of consistency, just reminding ourselves, you can treat these like one is red, one is green. Just as a reminder, hey, these are different dice. Event A is going to be that the green die shows a 3, and event B is going to be that the red and green dice together add up to 8. So let's find the probability of A given B. So the probability of A given B, if we just use that definition again, it's the probability that both occur, A and B, divided by the probability that just B occurs by itself. So keep in mind, again, if you want to write in A and B, if you want to say the green die shows 3 and the sum is 8, that's totally fine in here. But we can also just kind of keep it generic. Probably the easier thing to do is going to be to find the denominator, which is what's the likelihood of B occurring? What's the probability of B? So B is that the sum is 8. Now, we know from doing quite a few dice problems, these six-sided dice, right? We always assume, unless we're told otherwise, that they're six-sided. We know that there are 36 possible outcomes. So we just need to know, well, how many of those 36 give us a sum of 8? It turns out that 5 of them do, and we can kind of run through those for ourselves if we just want to keep in mind what those look like. So we could get 2 and 6, 6 and 2. We could have 3 and 5, 5 and 3. Again, because they're different dice, we need both orders there. And then we could have 4 and 4. And there's no other way to do this, right? We can't roll a 1, for example, because we wouldn't be able to get a 7 on the other die. So there are 5 ways out of 36 for us to just have a sum of 8 in some fashion. Okay, now the numerator, we want that sum of 8, so we want of those 5 possibilities, we want the green die to show a 3. So depending on how you order these, like I said, 2 and 6, 6 and 2. Well, okay, let's say that maybe the first one was our red and the second one was our green, right? So red, green, just to kind of keep everything organized. I should have maybe written that in one vertical list so it was a little bit more clear, or made a little table for myself. So the event A, the green die shows a 3, so let me just find anywhere where I see, okay, the green is a 3. Oh, it looks like just this one. So there's only one way that the green die is going to show a 3 and we have a sum of 8, right? It is just this one where the red is 5 and the green is 3. So again, this is the probability not just of these 5 among those 5 choices, but rather out of all 36 choices. There's only one way where the green die is exactly 3 and the sum is exactly 8, and it's that combination 5 and 3. So we can work through this, and kind of say, well, dividing by a fraction, I can multiply by the reciprocal. So this becomes times 36 over 5. Okay, my 36 on the bottom and top cancel out, and I get 1/5. So this is kind of the more formal way to do this. Of course, the alternative is to just kind of narrow your scope and say, okay, what are all the different ways to get a sum of 8? Right, and we did those 5. And then we say among those, right, given that we are in that group of 5, how many of our possibilities shown have the green die with 3? And so we only see that, again, that one case. So the one case out of the 5 for our narrowed set of outcomes, 1/5. Okay, so we didn't really need to reference back to the overall probabilities, but oftentimes it's a little bit easier to do that. But it generally is the case that we're going to see these denominators, this divided by 36, divided by 36. Oftentimes they're the same, and therefore they will cancel. So there's a couple ways to do those, but that's one way to go. Okay, and now I want to go back and reference independent events. So remember, we said independent meant that A occurring has no effect on the probability of B occurring. Okay, that's sort of, just sort of a nebulous thing. But what we're saying here is, and sorry, I should say that goes in both directions too. So B occurring should have no effect on the probability of A occurring. So two events, A and B, are going to be independent if they satisfy this equation. Basically, that the probability, you can almost think about skipping the middle step for a second here. The probability of A given B is equal to the probability of A. So basically, this is saying, hey, B has occurred, right? Given that B has occurred, find the probability of A. Well, if that's no different from just finding the probability of A without any extra conditions, that means that B didn't have any effect on the probability of A. B did not alter the outcome, the likelihood of the outcome of A at all. So that's what we're going to check in our example here. So we're going to say, okay, are the events in our previous example, so we're going to use the same A and B here, are they independent? So we already found out that the probability of A given B was 1/5. right? So we did the left side here. Now we just need to figure out, well, what was the probability of A all by itself? Okay, so remember, A is the green die shows a 3. Well, we know that we have, right, if it's just the green die, there are 6 outcomes for it, right? 1, 2, 3, 4, 5, 6. We don't have to say out of 36 because we're not referencing something happening with both dice. So just the one die. So what is the probability that the green die shows 3? Well, that can only happen one way out of those 6, right? If we roll a 3 and not any of the other 5 numbers. So then we look at these two and we say, okay, are these the same? So these are not equal. And we go up here and we say, well, in order for A and B to be independent, they would have to have the same probabilities, and yet they're different. So I guess this means they're not independent, otherwise known as dependent events. Right? Or if we're answering the question properly, are the events independent? No, they are not.